Thomas Haeberle worked with Dr. Bram Borison, and my understanding is that they were analyzing X-ray data. And so if I knew I was introducing you, I would have gone into a little more homework, but sorry about the technical difficulties. Thomas, are you ready to present? Do you have your
Yes,
slides there? Okay.
so my name is Thomas Haeberle. I spent the summer analyzing X-ray sources with Dr. Borison, and let me turn on my video. Okay, so yeah, so I spent the summer with him analyzing X-ray sources. I guess I could just get straight into sharing Firefox. Okay, so to give a little bit of a background on myself, since I didn't really do an introduction slide, basically I've been into stargazing my whole life, and sometimes, a lot of times, if I'm able to, if it's a clear enough night, I'll take out my telescope, and this is what it looks like. I got it, almost a year and a half ago at this point, in 2020. So, but I've used telescopes before. So I was already somewhat experienced, and now I have that. Now, unfortunately, looking at the stars in depth is kind of difficult where I am. It's in a great place called New York. I'm in a great place called New York City, where you can't really see anything. But when I am, in a dark spot, I can capture stuff like this on my camera that I actually started using this year. So back to that's enough, introduction. So basically what I've been studying this summer with Dr. Borison is X-ray sources, and they mainly come from neutron stars and black holes. And basically neutron stars, they're very small, oftentimes the size of like Manhattan Island. And they result from stars 1.4 times the mass of the sun, and it results from them dying in a supernova after fusing their heaviest element, which is iron. And the atoms inside these neutron stars are so squeezed together that the protons and electrons wind up fusing and they form neutrons, hence the name. And of course, all this mass inside of such a small object, it causes a very strong gravitational pull, which I'll get into later. It's enough to pull very massive stars. And so in more extreme cases, massive stars can supernova and turn into black holes. Basically, they're called stellar black holes. And as you might know, the gravity from these objects are so strong that not even light can escape their pull. And they also always appear at the center of galaxies, another fact that's common knowledge. And they're responsible, along with dark matter, for holding these galaxies together. So this is what your typical X-ray binary looks like. They tend to consist of a massive star or orbiting pretty closely to a black hole or a neutron star. And of course, the black hole or neutron star being so close, it pretty much sucks the gases from the star, and it slowly drains the life out of it. And so what I've been looking into as a NASA intern is the analysis of these sources, and these X-ray binaries. They generate a lot of X-rays, pretty much from the immense heat up of the accretion disk causes a lot of X-rays. So, and yeah, I've been analyzing these basically I've been looking at information such as NPSD and noise, and more significantly periods. And these periods are discovered when the amount of NPSD peaks at a certain frequency, and the shorter the frequency the graph peaks at, the longer said period is. Another important note would be that a graph can have multiple peaks. And as the frequency is shortened, the number of days in the period, they increase reciprocally. Some periods are still unknown, which my purpose as an intern was to discover some of the unknown periods using a software called Splat that essentially took data from a website, basically about 30,000 or so numbers, and it was able to compile it into one graph, which is how I analyzed it. And yeah, basically figuring out these periods will help us learn more about the X-ray sources. So what is MAXI and what's a light curve? MAXI is a Japanese X-ray telescope on the International Space Station. Over a period of hundreds of days, it can record data from systems and make a plot out of them. Basically, like what I said before, they're put on the website. I can just select all the numbers, put them into software called Splat, and everything just kind of shows. It's easy to read, and it puts time on the x-axis most of the time, and brightness on the y-axis, and the graph is just known as a light curve. So we are studying X-rays because not much is known about them as other branches of astronomy. Oh, accidentally. They are mysterious. They're mysterious in that we are still trying to learn why they peak at certain points. And so this kind of shows a sample of a bit of the spreadsheet I was doing. So basically what I've been doing is gathering the data for a lot of these X-ray sources and plotting them on this spreadsheet, this one big spreadsheet, which I can show a screenshot of in a moment. And so you can see your typical graph in the corner. It shows it's a graph of SMC X1, which is an X-ray source in the Small Magellanic Cloud. It has about 4 or so very noticeable peaks in the graph that I have marked with red arrows. And this is pretty much, this isn't the whole thing, but it shows all the different columns, basically peaks for, frequency, which is hertz, the periods, NPSD. And basically to explain some of it, some of the sources I analyzed in more detail than others. Some of the sources like SMCX3 are a lot less detailed. That's why they have an exponent for the NPSD. And those were analyzed just using the website. While for the highlighted ones, I used Splat. That was when I figured out Splat, and it shows a lot more detail. And this isn't, like I said, this isn't all of the, this isn't every system I analyzed. There's actually about 200 or so in the entire spreadsheet. And only about, I'd say 70 of them were analyzed in the highlighted detail. And so some noticeable artifacts I've noticed. A lot of these systems actually have a peak at 73 days, also known as, 10 to the negative 6.8 hertz. And we realized, me and Dr. Borison realized that was because the telescope itself actually has movement every 73 days. So that was, that was something to note. And some systems also have peaks at 36 and 23 days, which I believe they're called harmonics, which might be an effect from the 73-day period wobble.
Hey, Thomas, I'm just interrupting to say you have about 1 minute left.
Oh, there was a limit. Okay, well, all right.
Little wiggle room there, but I'm moving it along.
Yeah. All right, sorry about that. Well, I'm gonna try to speed through the rest of it then. Doing research was made easy by this website, ADS. Oh, this is actually the last slide. In the future, it should be known that analyzing the sources with MAXI was very convenient, and especially Splat made it easy. And it could lead, I think that telescope can also lead us to new discoveries. And if a new period is found, I think it would be noted that another telescope could be used to verify the source and maybe analyze it a bit more. That's it. Questions?
Okay, well, thank you very much. Let's have some applause for our speaker.